In this clip, we introduce a method of multiplying by 5 using our hands as a calculator. We're going to start with 2 closed fists. And we're going to count up to the multiplier. The multiplier is always 5. The multiplier, we're going to count up to, starting on the right, I want to multiply 5 times 2. So I'm going to count 1, starting on the right hand, and then going to the left, 2. Okay. So there's the multiplier. This represents 5 times 2. I'm going to compare the 2 sets. 1 is equal to 1. So the right hand, if the sets are equal, the right hand equals 0. The left hand represents the tens place. So I have 1, 0. You can close all the fingers if you want, but it's much more difficult for me to do it, using the model. But you can do it. Close your hand, close the right hand, and that represents 0, and this represents 1. So 5 times 2 is 10. 5 times 3, here's 1, 2, 3. Okay? We're going to alternate the count up to the multiplier. Then we're going to compare the 2 sets. 2 is not equal to 1. The sets are not equal. We are going to open the right hand. It now represents 5. Okay? I'll do it once. You can do it much easier than me. You can just open them. We have 1, 2, 3. The sets are not equal. Open your right hand. You have a 1 and a 5. So 5 times 3 is 15. 1, 5. 5 times 4, I have 1, 2, 3, 4. The sets are equal. 2 is equal to 2. Right hand represents 0. Left hand represents the tens place. So I have 2, 0, 20. 5 times 4 is 20. 5 times 5, I have 5 times 4 shown here. The count goes 1, 2, 3, 4. You're always going to start with the right hand and alternate. So there's 5. So I have 3 extended fingers on the right and 2 on the left. The sets are not equal. This right hand now represents a 5. The left hand is the tens place, so it's a 2 and a 5. So 5 times 5 is 25. 5 times 6, I go back. This is 1, 2, 3, 4, 5, and then 6. 5 times 6. So I have 3 extended fingers on the left and 3 extended fingers on the right. The sets are equal. That means the right hand is a 0. So 5 times 6 is 3, 0, 30. 5 times 6 is 30. 7, I'm going to raise this. But what we do is, American Sign Language now, we'll raise those 2 and close the thumb. So I have 3 on the left and 4 on the right. The sets are not equal. That means this is a 5. The right hand is a 5, and this is a 3. So 5 times 7 is 35. 5 times 8, I have to raise these 2, and close the thumb. That's 8. So the sets are equal. 4 is equal to 4. That means the right hand is a 0. So I have 4 in the left, that's the tens place. So 8 times 5 is 40. Finally, 9, and here's 9. The sets 5 is not equal to 4, so the sets are not equal. I'm going to open my right hand, which is already open. So 9 times 5 is 45. So about the 5s. If it's an even number, 2, 4, 6, and 8, the right hand is going to be a 0. If it's an odd number, 3, 5, 7, or 9, the right hand is going to represent 5. And the left hand always represents the tens number. In this clip, we will demonstrate why multiplication by 5 using our hands as a calculator will give us an accurate result. Trachtenberg arithmetic. This is the multiplier 5 all the way down, and these are the multiplicons 2, 3, all the way up to 9, from 2 to 9. Trachtenberg invented a system of arithmetic where you can get the product of two numbers by doing simple operations on the multiplicon. If you want to multiply 5 times 2, he says take 2, the multiplicon, divide by 2, and you get the tens place, 1. If 2 is an even number, then the ones place is a 0. Multiplicon 3, you must divide by 2, you're going to get 1.5. He says drop the fraction. So it becomes 1. This is a 1. There it is, the tens place. And because 3 is an odd number, then the ones place is a 5. And so multiplicon 2, 4, 6, and 8, the ones place is a 0. For multiplicon 3, 5, 7, and 9, the ones place is going to be a 5. Now we can duplicate this pencil and paper arithmetic by using our hands as a calculator. The hands now represent 5 times 2. We start with a closed fist, and the count goes like this. 1, extend one finger in the right hand, always the right hand first, and then alternate to the left hand and extend a finger. 2. We count up to the multiplicon. We can demonstrate when we get an even, when the sets are equal, 1 is equal to 1. If we just close the right hand, and that represents 0, it's not easy to do with the model. We have 1, and then we compare it to this 1, and it's equal. Just close it. Very easy to do with your hand, not so easy to do with the model. So there it is, 1, 0. So we get 10. The hands now represent 5 times 5. The count goes like this. 1, 2, 3, 4, 5. Then we compare the two sets. 3 extended on the right, 2 extended on the left. The sets are not equal. That means 5 is an odd number. And the right hand now is going to represent 5. And the way we can do that, I open the right hand. It shows 2, 5. So 5 times 5 is 25. This is the tens place. This is the ones place. So we've done this operation by alternating the count. 5 divided by 2, we just get a 2, not 2.5. And by opening the right hand, we get that 5 because the sets were not equal. 2, 5, 25. 5 times 5 is 25. So the hands are superior to pencil and paper arithmetic. We want to complete the products in the multiplication table. We have studied how to multiply by 5. There's all the 5s. 6, there's all the 6s. Visual 9 gives us all the 9s. And tens complement gives us all the high numbers. So we know 4 methods. What we want is all the products from 10 to 81. And we're missing these 2 and these 6. Trachtenberg 3, 4, 7, and 8 as multipliers are too difficult. There's too many mental steps that have to be taken in order to do it accurately using your hands. So we're not going to bother. We're going to get these by addition. Get what we need by addition. Trachtenberg 2 says take the multiplicand 4 and double it. So 4 times 4 is 8. So what is 3 times 4? All I have to do is take that 8 and add 4 to it and I get a 12. 4 times 4? All I have to do is take that 12 and add 4 to it and I get 16. So we have these 2 blocks and we got it by addition. 7 and 7 is 14, 8 and 8 is 16, but there's an easier way of doing it. 6 times 2 first. And the hands represent 6 times 2. The count always starts with the right hand. 1, 2. Next we compare the finger sets. The sets are equal. 1's equal to 1. We don't have to add anything. If the sets are not equal, we have to add a 5. The 1's place is a 2. The multiplicand, there it is, 2. The 10's place is the open finger set in the left hand, 1. So we have 6 times 2 is 12. Now to get 7 times 2, all we need to do is add 2 to 12 and we get 14. All we need to do to get 8 times 2 is add 2 to 14 and we get 16. So we have these 2. That's a little easier than adding 7 and 7 and 8 and 8. Next we want to find 7 times 3 and 8 times 3, these 2. So we're going to use 6 times 3 first. The hands now represent 6 times 3. The count is 1, 2, 3. The sets are not equal, so we have to add 5. So 3 and 5 is 8. So the 1's place is an 8. The 10's place is always the open finger set in the left hand, 1. So 6 times 3 is 18. To get 7 times 3, all I need to do is add 3 to 18, I get 21. To get 8 times 3, all I have to do is add 3 to 21 and I get 24. So we have these 2. 7 times 4. The hands now represent 6 times 4. The count goes like this. Start at the right, count up to the multiplicand. 1, 2, 3, 4. Then we compare the 2 sets. 2 is equal to 2, so we don't have to add anything. 1's place is the multiplicand, 4. There it is. The 10's place is the open finger set in the left hand, 2. So 6 times 4 is 24. In order to get 7 times 4, all I need to do is add 4 to 24, I get 28. All I need to do is to add 4 to 28 and I get 32. So we have all the products now in the multiplication table from 10 to 81. 8 of them, these 6, and 2 is 8. We did by addition. Anyway, that ends it. We have all the products in the multiplication table now from 10 to 81. Using our hands as a calculator is very useful. And every student in K-12 should be taught to use their hands as a calculator because it's already built in. It's a natural computer, if you will. And there's no reason why they should memorize the multiplication table when they can verify it using their hands as a calculator.